This next slide shows why we bother with making acetylide ions, reacting something like ethyne here with an amide ion. It's because they become great nucleophiles. And if you think back to what we just dealt with back in chapter 8, we talked about a number of things that behave as nucleophiles, and here's yet another one to add to the list. And when you can create a nucleophile that contains carbon, that's particularly useful in chemistry because you can cause that carbon that starts off as being part of an alkyne to be incorporated into a larger molecule where it's connected to a carbon that starts off in a separate molecule. So you can build more elaborate structures, longer carbon chains, starting with molecules that have short carbon chains. And that's of very much great use in the world of organic chemistry. Now the amide here, the NH2, is normally going to be supplied as its sodium salt, sodium amide here. And because amide is so reactive with plain water, you have to do this in special solvent. NH3 ammonia is a gas at room temperature, but if you cool it down enough to about -33°C, you can liquefy it and it can be used as a solvent. And so we have ammonia as our solvent, and we've dissolved this anion, sodium amide, and now we can introduce an alkyne as long as it's a so-called terminal alkyne, meaning the triple bond has to be at the end of the chain so that there is at least one carbon-hydrogen bond that can be removed. If we were doing this with, say, 2-butene or something where the triple bond is in the middle of the molecule, this wouldn't work because those carbons would not be directly connected to hydrogen. But we create here what we could call sodium acetylide, but it's that negatively charged carbon that's the important part here. And in this second reaction, we can react it with a large number of alkyl halides. As it says there, the R here has to be something simple like methyl or a primary alkyl halide. But we could choose for that alkyl halide to have a specific number of carbons, and we could plan ahead and make a chain that has a certain total number of carbons. And it's, of course, going to maintain that triple bond somewhere. So we'll see some examples of this later. And we're going to talk soon about other reactions involving that carbon-carbon triple bond, but addition reactions, in fact, similar to what alkenes do. When you add chlorine across a double bond, you can do that kind of thing with triple bonds as well. But this is a general example of what we can do with alkynes as far as making them behave as good nucleophiles. Now the limitation mentioned on that last slide is that the alkyl halide has to be primary, and if it's not, then you can see it shows you here what happens. Acetylide is a very good nucleophile, meaning it's good at making bonds to carbons, but it's also a very good base. And in organic chemistry, base means that it can remove hydrogens from things like alkyl halides. And so you can see here the effect would be to take our acetylide ion and turn it back into the acetylene that it started off as. So that happens, as it says, with secondary or tertiary halides. And so this is a competing reaction. We may want a simple substitution to occur, but sometimes we get a hydrogen added back here to our acetylide ion. But as long as the alkyl halide is primary, then we get the intended type of reaction.